Good afternoon, everyone. My name is Jing Yuan. I'm from UT Dallas. In this talk, I will present this first paper for the authors because they cannot be here because of the visa problems. Okay. So this work is done by Dr. Haiming Jin, Professor Lu Su, and Professor Clara Nasdaq. In this work, the authors study the problem of incentivizing truth discovery in mobile crowd-sensing systems. Okay. So we have all experienced the recent popularity of mobile crowd-sensing systems, which utilize the public crowd equipped with various types of mobile devices, such as a smartphone, smartwatch, smart glass, and so on for large-scale sensing tasks. So one example of such mobile crowd sensing system is the US FDA-approved MedWatcher system, where a cloud-based platform requires participants to submit photos of their medical devices and analyze the collected photos to help identify visible problems with the medical devices. Apart from healthcare, applications of MCS systems have pervaded almost every corner of our everyday living and working, including smart transportation, indoor localization, environmental monitoring, and so on. Okay. However, crowd-sensing systems are confronted with a major challenge that individual workers' sensory data are unreliable. Because of lack of effort, insufficient skill, poor sensory quality, environmental noise, lack of sensor collaboration, and so on. Thus, we need to carefully aggregate workers' noisy or even conflicting sensory data to discover the underlying truth when users' the quality is unknown a priori. Okay? So address this problem, a family of algorithms called truth discovery have been proposed and widely studied. A truth algorithm typically takes workers' sensory data as input and output the estimated ground truth based on the principles that a worker is reliable if she provides many pieces of true information. And a piece of information is likely to be true if it's provided by many high-quality workers. However, in practice, low sensing effort leads to low data quality. Therefore, the goal of this work is to design a payment mechanism that incentivizes high-effort sensing from workers so that the estimated ground truths calculated by truth algorithms are highly accurate. Okay. The architecture of the mobile crowd-sensing systems considered in this work consists of a cloud-based platform and a set of crowd workers. The workflow of such system is as follows. First, the platform announces the payment mechanism to workers. Next, the workers decide the level of their sensing effort, carry out sensing, and submit their sensory data to the platform. After receiving workers' data, the platform calculates payments according to the payment mechanism and send the payments to the participating workers. Next, we introduce the general procedure of truth discovery algorithms. So such an algorithm is basically an iterative procedure, which in each iteration firstly fix the estimated ground truth and set each worker's weight to be negatively correlated to the distance between her data and the ground truth. And then it fixes workers' weights and estimate the ground truth by calculating a weighted sum of the sensory data. Such iterations are run until convergence. As previously mentioned, the workflow of mobile crowd-sensing system starts with the platform announcing the payment mechanism to workers, which calculates the payment to workers based on the set of collected sensory data. It then induces a non-cooperative game among the workers, which is referred to as sensing game. The authors assume that the difference between any worker's data and the ground truth follows a zero-mean Gaussian distribution with standard deviation delta. Furthermore, they assume that standard deviation is bounded and monotonely decreases with the worker's effort level. Thus, to simplify presentation, the authors use standard deviation delta S instead of the effort level ES as a worker's strategy. Specifically, delta S means the worker S chooses not to participate. Therefore, a worker's gain is simply the payment she gets from the platform minus her cost from sensing. Next, I'll introduce the design objectives of the payment algorithm, which are threefold. The first goal is individual rationality, which means that no worker has negative expected gain at the Bayesian Nash equilibrium. And the Bayesian Nash equilibrium, or BNE for short, is a strategy profile such that each worker S maximizes her expected gain by taking the strategy specified by the BNE, given that other workers take their BNE strategies. Okay. The second design goal is the budget feasibility, which means the platform's expected overall payment at the BNE does not go beyond budget B. The third design goal is low error probability. In this work, the error probability of a truth discovery algorithm is defined as a probability that the mean absolute error is no less than a given threshold alpha. Before I introduce the formulation of the payment mechanism design problem, I'll introduce lemma 1, which the formulation is based on. Lemma 1 basically states that given any positive alpha, the strategy profile we have an upper bound of the error probability that is proportional to the sum of participating workers' standard deviations. Thus, it indicates that, Lemma 1 basically states that given any positive alpha and strategy profile, we have an upper bound of the error probability that is proportional to the sum of participating workers' standard deviations. Thus, it indicates that minimizing the upper bound of the error probability given in lemma 1 is equivalent to minimizing this sum. Thus, payment mechanism design problem is formulated as this optimization program, where P denotes the set of all payments mechanisms so that the sensing game has a BNE. B represents the platform's budget, and S represents the set of workers. The variable of the PMD problem is a payment mechanism P. Furthermore, delta star denotes the BNE corresponding to P, and S prime and X delta star denotes, respectively, the set of workers that choose to participate and a set of collected sensory data at the BNE. Therefore, the PMD problem ensures budget feasibility and individual rationality and minimize the upper bound of the error probability given by lemma 1 at the BNE. As solving the PMD problem to obtain the optimal payment mechanism is very hard, the authors propose their own payment mechanism called Theseus. The name Theseus comes from incentivizing truth discovery with strategic data sources. Okay. Theseus takes as input the task set, the worker set, participating worker set, collected sensory data, as well as the predefined parameter AS and BS for each worker S. For each participating worker S, the algorithm set payment PS to be negatively correlated to the difference between the worker S data and that of a random picked reference worker R. Clearly, if any worker S chooses not to participate, her payment is set at 0. Then the question left to be answered is how the parameters AS and BS should be selected for each worker S. So next, I'll first introduce two more assumptions, which the author's parameterization is based on. The authors assume that each worker S cost is linear in a standard deviation. Furthermore, they assume that the lower bounds of each worker standard deviation, that is delta 1, delta 2 through delta S, are bounded IID, random variables, with a known PDF. The others study the parameterization of Theseus in the following two scenarios, namely complete information scenario, where the platform knows exactly each worker's cost, CS1 and CS2, and the incomplete information scenario, where the platform only knows the range of each worker's CS1 and CS2. Because of time limit, I'll only introduce the complete information scenario in this presentation. For those of you who are interested in the incomplete information scenario, please refer to the paper. So in the complete information case, the authors propose to parameterize Theseus with a set of parameters AS and BS that satisfy the following condition 1 through 3. Okay. Where A delta t denotes this integral, and delta t is an extra parameter introduced in condition 2. In next few slides, I'll introduce the author's theoretical results about parameterizing Theseus according to these conditions. In Theorem 1, the authors prove that the parameters A and BS satisfy condition 1 and 2, then the strategy profile given in this theorem is a BNE of the sensing game. By Theorem 1 at the BNE, every worker S with delta S greater than delta T will drop out on their own decision. And as long as delta S, which is less than delta T, the worker will participate with the smallest standard deviation, delta S. In Theorem 2, authors prove that condition 3 ensures that Theseus satisfies budget feasibility. Furthermore, they prove in Theorem 3 that Theseus satisfies individual rationality as well. So next, I'll introduce the selection of the additional parameter delta t so that Theseus could bear other desirable properties. In Theorem 4, the authors prove that given any theta c, which is in the interval between 0 and 1, if delta t is greater than the transverse function f on 1 minus s square root 1 minus theta c, then the probability that the minimum value among delta 1, delta 2 through delta s is no greater than delta t will be lower bounded by theta s, which indicates that the probability that there exists at least one participating worker at the BNE of the sensing game is no less than theta c as well. Theorem 4 basically estimates a lower bound for delta t. In Theorem 5, the authors prove that given any alpha c greater than 1 and beta c in 0 and 1, if delta t is less than delta t bar, then the probability that the ratio between the value of a PMD problem's objective function given by Theseus and the minimum payment is no less than alpha c will be upper bounded by beta c. Theorem 5 gives us a probabilistic guarantee on the approximation ratio of Theseus compared to the optimal payment mechanism, and established an upper bound for delta t. In summary, in the complete information case, if the parameters AS and BS satisfy condition 1 through 3, then and delta t is selected according to Theorem 4 and 5, then the mechanism Theseus satisfies budget feasibility, individual rationality, as well as with high probability that it has a small approximation ratio, and with high probability it guarantees that there exist participating workers. In the others' simulation, they compare Theseus with two baseline methods, including max STD, where each worker as strategy is the maximum value of their standard deviation, and random STD, where each worker as choose their strategy uniformly at random. From the simulation result, we can easily observe that Theseus reduces the MAE of truth discovery algorithm compared to the two baseline methods. Okay, to sum up, in this paper, the authors propose a payment mechanism called Theseus, which is used in pair with the truth discovery algorithm to ensure high aggregation accuracy in MCS system, where workers may strategically reduce their sensing effort. Okay? Theseus incentivizes workers to spend their maximum sensing effort and bears other desirable properties, including individual rationality and budget feasibility. An acknowledgement to make before I conclude this presentation is that this work was primarily funded by the National Science Foundation of China, Trustworthy Health and Wellness. Okay, so this is about this presentation. Thank you so much for your attention. Okay.